On April 13, 2024, Iran launched one of the most complex aerial attacks in modern military history. 170 drones, 120 ballistic missiles, and 30 cruise missiles, all fired simultaneously at Israeli military installations. The strike cost Iran between $80 and $100 million to execute. The result? A 99% intercept rate. Not a single major installation was destroyed. The science that stopped that attack: layered missile defense systems, real-time tracking algorithms, directed energy prototypes, and multinational sensor fusion, performed in ways that would have seemed like science fiction just 20 years ago. But here's the number that matters most. It cost Israel and its allies approximately $1 billion to stop an $80 million attack. The offense cost $80 million. The defense cost $1 billion. That single statistic captures the central tension of modern military science, and it's the question we're going to spend the next 10 minutes exploring. How does science shape the weapons of war? What happens when physics, mathematics, artificial intelligence, and materials science converge in the most high-stakes engineering environment on Earth? And where is the science of warfare heading next? The science of speed. Hypersonic weapons. 1 to 3. Let's start with what is arguably the single most consequential scientific development in modern military technology: hypersonic weapons. The word hypersonic refers to speeds exceeding Mach 5, that is, 5 times the speed of sound, or roughly 6,100 kilometers per hour. At that velocity, a missile launched from the coast of China can reach the western coast of the United States in under 30 minutes. A weapon fired from the North Sea can reach London in seconds. Decision-making timelines that used to be measured in hours collapse to minutes, and sometimes to seconds. To understand why this is scientifically remarkable, consider what happens to matter at hypersonic velocities. At Mach 5 and above, aerodynamic heating becomes so intense that the air molecules around the vehicle begin to ionize, forming a superheated plasma sheath around the weapon. This plasma causes radio frequency blackouts, making it nearly impossible for the missile to receive GPS signals or communicate with its operators. The vehicle must navigate autonomously, using inertial guidance systems that rely on onboard accelerometers and gyroscopes, instruments so precise they can track position changes measured in fractions of a millimeter per second. The G-forces involved in the high-speed maneuvers these weapons perform place extraordinary demands on structural materials. Engineers have turned to carbon-carbon composites, ultra-high-temperature ceramics, and advanced thermal protection systems borrowed directly from the Space Shuttle program to keep hypersonic glide vehicles from disintegrating. The United States, Russia, and China are all actively developing and testing hypersonic weapon systems. Russia has claimed operational deployment of the Avangard hypersonic glide vehicle and the Kinzhal air-launched hypersonic missile. China has demonstrated sophisticated fractional orbital bombardment systems, weapons that travel partly in low Earth orbit before descending on their targets, approaching from directions that traditional radar networks are not designed to watch. The U.S. Army's long-range hypersonic weapon, known as Dark Eagle, is progressing through limited testing and integration as of 2026. Japan, with a $2 billion allocation under its Acquisition Technology and Logistics Agency, has contracted Mitsubishi Heavy Industries to develop both a hypersonic cruise missile and a hypervelocity gliding projectile, the latter expected to enter service around 2026. The science arms race around hypersonics is global, accelerating, and represents the sharpest leading edge of applied physics in any engineering program on Earth today. Defending against these weapons is where the scientific challenge becomes almost philosophically daunting. Detection requires sensor networks capable of tracking an extremely fast, unpredictably maneuvering target from launch to impact, across thousands of kilometers in real time. Interception requires a defensive missile that can match the hypersonic vehicle's speed and agility, while the hypersonic vehicle is actively trying to evade it. The physics of the intercept problem are extraordinarily demanding, and as of today, no nation has demonstrated a reliable operational capability to intercept a hypersonic glide vehicle in flight. Section 2. The Science of Light. Directed Energy Weapons. 3 to 5. If hypersonic weapons represent the science of extreme speed, directed energy weapons represent something even more fundamental: the science of light itself. A directed energy weapon, or DEDU, is any system that uses focused electromagnetic energy rather than a physical projectile to damage or destroy a target. This category includes high-energy lasers, high-power microwave systems, and particle beam weapons. The concept is ancient. Legend attributes a version of the idea to Archimedes, who allegedly used a system of mirrors to focus sunlight and ignite Roman warships during the siege of Syracuse. The modern engineering reality is rather more sophisticated. High-energy laser weapons work on a simple but brutally elegant principle: focus enough photons on a small enough area for long enough, and the thermal energy deposited causes catastrophic structural failure. A 100-kilowatt laser, the approximate power class of Israel's Iron Beam system, which was set for deployment in late 2025 to counter rockets and drones, can heat the skin of an incoming drone to failure point in under 3 seconds at ranges of several kilometers. The UK's RFDEDU system, the radio frequency directed energy weapon, achieved something even more striking from an economic standpoint. It successfully shot down drone targets at a cost of approximately 13 cents per shot. 13 cents to destroy a target that might cost tens of thousands of dollars to build and launch. That economic asymmetry is transformative. For every expensive interceptor missile a defense system fires to stop a cheap drone, an adversary wins an economic war of attrition. A directed energy weapon that fires at the cost of electricity fundamentally rewrites that equation. High-power microwave weapons operate on a different scientific principle. Instead of heating the target's skin, they penetrate inside electronic systems and fry the circuitry. India's Defense Research and Development Organization unveiled a high-power microwave system in January 2026 at the International Conference on Electronic Warfare, reporting that in testing it had already disabled small quadcopter drones and DJI Phantom-class UAVs at ranges up to 1 kilometer, with a goal of reaching 5 kilometers by the time testing concludes in June 2026. The system operates in the S-band frequency, with a maximum power output of 450 megawatts in 20 nanosecond pulses. That number, 450 megawatts, is roughly the output of a medium-sized nuclear power plant, delivered in a pulse shorter than the blink of an eye. The engineering challenges of directed energy weapons are formidable. High-energy lasers are highly sensitive to atmospheric conditions. Moisture, dust, smoke, and turbulence all scatter and absorb photons, reducing effective range. Thermal management is a critical design problem. Powerful lasers generate enormous waste heat that must be removed quickly or the system damages itself. Power systems capable of delivering sustained high-energy output in a mobile military platform represent one of the most demanding electrical engineering challenges in the field. It is advances in power management, directly inspired by electric vehicle battery technology, that are now accelerating the practical deployment of directed energy weapons after decades of promising laboratory results that failed to translate to battlefield reality. Section 3. The Science of Decision. Artificial Intelligence in Warfare. 5 to 7. Of all the scientific forces reshaping modern warfare, none is moving faster or carrying deeper implications than artificial intelligence. In November 2025, U.S. Defense Secretary Pete Hegseth announced that the Department of Defense was narrowing its technology development focus to 6 priority areas, and artificial intelligence was explicitly named as one of them. The DoD's commitment to AI spans 2 distinct but interconnected domains: AI for warfighting, autonomous weapons, target recognition, real-time battlefield decision support, and AI for enterprise operations, including logistics, maintenance prediction, and intelligence analysis. Project Maven is among the most publicly known examples of AI applied to military intelligence. Launched by the Pentagon, Maven uses machine learning systems to analyze vast quantities of drone surveillance footage, footage that would take thousands of human analysts years to review manually, and automatically identify objects of military significance: vehicles, weapon systems, personnel movements, and infrastructure. The same computer vision science that powers facial recognition in your smartphone has been adapted to recognize the thermal signature of a tank engine from 10,000 feet in the middle of the night. Autonomous weapon systems. What the defense community calls lethal autonomous weapon systems, or LAWs, represent the most ethically charged application of AI in warfare. A drone swarm, for example, can consist of hundreds or thousands of small, relatively inexpensive unmanned vehicles, each carrying sensors and processing capability, collectively sharing information and coordinating behavior through emergent algorithms. The collective capability of a swarm significantly exceeds the sum of its individual platforms. A swarm can overwhelm conventional point defense systems through sheer numerical saturation. There are simply not enough interceptors to stop hundreds of simultaneously attacking vehicles. In March 2025, the U.S. Air Force revealed its first completely unmanned fighter jets, the YFQ-42A and YFQ-44A, aircraft capable of autonomous flight and solo combat missions, with the YFQ-44A capable of cruising at 50,000 feet at speeds exceeding 650 miles per hour. These are not remote-controlled aircraft. They are aircraft that can make tactical decisions in flight faster than any human pilot could react. The science underpinning this capability, reinforcement learning, computer vision, sensor fusion, edge computing, was developed almost entirely in the civilian technology sector. The algorithms that teach autonomous military systems to navigate, identify targets, and make engagement decisions are close relatives of the algorithms that teach self-driving cars to navigate traffic. This blurring of the boundary between civilian technology research and military application is one of the defining characteristics of the current era of military science, and one of its deepest ethical challenges. Section 4. The Science of Materials. From Railguns to Self-Healing Armor. 7 to 845. Beyond the headline technologies of hypersonics, directed energy, and AI, there is a quieter but equally profound scientific revolution happening at the materials level, in the laboratories where physicists and engineers are working on what weapons and soldiers are literally made of. The electromagnetic railgun is one of the most scientifically striking examples. A railgun uses powerful magnetic fields generated by enormous pulses of electrical current through parallel conducting rails to accelerate a projectile to hypersonic velocities without any chemical explosive. The physics are elegant. The Lorentz force, the same fundamental electromagnetic force that drives electric motors, accelerates a conductive armature riding between the rails to velocities of Mach 6 or higher. In 2023, a feasibility study by the European Defence Agency identified a future railgun capable of firing a projectile at Mach 6, 10 times faster than most aircraft, with testing on a firing range targeted for 2028. The military implications are significant. Railgun projectiles don't require explosive warheads, making them cheaper and dramatically safer to store aboard warships. And the range is achievable, potentially hundreds of kilometers, could fundamentally change the calculus of naval warfare. At the opposite end of the scale, advances in biotechnology and nanotechnology are producing materials with properties that would have seemed fantastical a decade ago. Self-healing armor. Composite materials that can automatically repair minor damage to their structural integrity is emerging from defense materials research programs as a genuine near-term capability. The Internet of Military Things, or IOMT, embeds sensors and computing power directly into soldiers' equipment, clothing, helmets, body armor, creating a real-time data network that monitors physiological status, environmental conditions, and tactical information simultaneously. A soldier's body armor in 2026 is not just a passive physical barrier. It is an active sensor platform, transmitting data to commanders and receiving targeting information in return. Section 5. The Science of Deterrence. Where all this leads. 8:45 to 10:15. Here is where a scientist's view of war becomes genuinely sobering. Every technology we have discussed, hypersonic missiles, directed energy weapons, autonomous AI systems, space-based weapons, was developed with the stated purpose of providing security, protecting populations, deterring aggression, and maintaining strategic stability. And yet, the collective effect of all these technologies, arriving simultaneously and proliferating across multiple nation-states at unprecedented speed, is to compress decision-making timelines to levels that stress the ability of any human political system to respond with adequate deliberation. When a hypersonic weapon can reach its target in under 10 minutes, the window for diplomatic de-escalation during a crisis shrinks to near zero. When autonomous systems can initiate and prosecute engagements faster than a human commander can authorize them, the traditional chain of command, which is also the mechanism by which international humanitarian law is supposed to constrain warfare, is placed under extraordinary pressure. The theoretical underpinning of nuclear deterrence, mutually assured destruction, assumed that both sides had enough warning time to recognize an attack and respond. Fractional orbital bombardment systems and hypersonic glide vehicles, approaching from unexpected directions at unprecedented speeds, are explicitly designed to shrink or eliminate that warning time. The economic asymmetry we noted at the beginning, $1 billion to stop an $80 million attack, points to a deeper strategic paradox. If offense becomes structurally cheaper than defense, the rational calculus of warfare shifts in ways that have historically preceded major conflicts. The proliferation of cheap drone technology, combined with the difficulty of defending against mass drone swarms with expensive interceptors, is a version of this problem that the Iran War of 2026 has brought into sharp relief. The scientific creativity that produced these weapons has, in many cases, run ahead of the strategic and legal frameworks designed to govern their use. A scientist's view of war is, in the end, a view of human ingenuity operating under its most extreme constraints and incentives, and arriving at solutions that are simultaneously brilliant and terrifying. The same quantum mechanics that describes the behavior of electrons in a semiconductor also describes the behavior of a nuclear warhead. The same material science that builds lighter aircraft for commercial aviation builds lighter munitions for combat. The same artificial intelligence that recommends your next streaming show, trained on vast quantities of human-generated data, is being trained on vast quantities of tactical data to make autonomous engagement decisions on battlefields. The technologies we covered today, hypersonic weapons traveling at Mach 5 and beyond, directed energy systems firing at the cost of electricity, AI-driven autonomous weapons capable of drone swarm tactics, railguns powered by electromagnetic physics, self-healing armor embedded with sensor networks, represent the current scientific frontier of warfare. They are not hypothetical. They are in testing, in production, or already deployed. The U.S. Department of Defense's top 6 technology priorities for 2026 explicitly include artificial intelligence, hypersonic weapons, and counter-drone systems. The Golden Dome missile defense program secured $25 billion in initial funding. Every major military power on Earth is racing to develop, field, and counter these systems simultaneously. What makes a scientist's view of war uniquely valuable is not just technical understanding of these systems. It is the recognition that every advance in offensive capability creates a new problem in defensive capability, and that the cycle of action and reaction is, historically, one of the most reliable engines of escalation that human civilization has ever produced. The question that science cannot answer, but that every one of us must confront, is whether the political, diplomatic, and legal frameworks we have built to govern warfare can keep pace with the scientific frameworks we have built to conduct it. That gap, more than any single weapon system, may be the most important security challenge of the 21st century. If this documentary breakdown gave you a clearer picture of the science behind modern warfare, please hit the like button. It helps this kind of in-depth educational content reach a wider audience. Subscribe so you don't miss our next deep dive, and drop a comment below. Which of these technologies do you think carries the most profound implications for the future? Hypersonics, AI autonomy, or directed energy? I read every comment. I'm your name, and I'll see you in the next one.